Hello everybody, and a special thanks to the organizers of the third International Electronic Conferences on Geosciences for providing such an opportunity to share our contribution in a single platform. Our research is entitled GIS-based groundwater potentiality mapping using AHP and FR models in central Antalya in Turkey. In this presentation, I would like to give brief information about the study area and objectives of the research, and as well as the methodology, the concept of analytical hierarchy process or AHP, and the generation of the special data sets, consequently the concept of the frequency ratio, as well as the presentation will continue to the results and discussion of this research, and will end it by the conclusions. The members of this research has been selected differently from different disciplines and fields. So our supervisor, and as well as a geologist, hydrogeologist, computer engineer, and as well as map engineer. So basically the subject of this research is the groundwater, the potentiality of the groundwater. For now, in recent times, groundwater is considered as one of the essential natural resources beneath the earth, which have been accumulated by infiltration through various rock layers, and as well as due to the rapid growth of industrialization and population demands on fresh waters, which have been directly affected on groundwater, has been increasing, which nowadays it's considered a worldwide concern. Therefore, the exploration of groundwater is considered as an essential part of groundwater management and planning. So different types of or different techniques are available for mapping of the groundwater potentiality mapping or groundwater exploration, but they are different. Their results are different, their implementation are different. The conventional methods are considered time consuming and cost expensive. So in the recent time, different algorithms are applied using the remote sensing and GIS techniques to delineate the groundwater potentiality mapping. In this research, based on the demands, groundwater demands and exploration of the groundwater, three objectives have been set. The first and the very crucial is to delineate the groundwater potential zones within the central Antalya using the AHP and FR models, and as well as to highlight the capability of the AHP and FR models in groundwater potentiality. So as it's clear that these two models have been applied in different disciplines, so in this research we have made efforts to highlight or demonstrate the capability of these two models in this relevant discipline, and as well as to consider the role of the remote sensing and GIS in handling of AHP and FR models. Our study area is located in the southwest of the Turkey, with the area of about 4,060 square kilometer. It's concluded for district Korkutali, Dushimaltı, Kapız, Muratpaşa, and Konyaaltı. And as well as in the northern part, this our study area is bordered with Denizli, Isparta, Burdur, and also the Turkish mountains. And in the southeast, it's bordered with the Mediterranean east. So generally, the climate of this study area is Mediterranean. It means that it's characterized by hot and dry summer and rainy and warm winter. Based on the objective of this research, the methodology of this research has been designed. Generally, three types of data has been used to accomplish the objective of this research: the satellite imagery, conventional data, and climatic data. Their process from the three types of satellite imagery has been used consequently: digital elevation models, Sentinel-2 and Landsat-8. From DM, lineament density map, and renal density have been generated, and from Sentinel-2 and Landsat-8, after the pre-processing of these, some other thematic layer such as the land cover and land use layers has been generated. From conventional data, geological and lithological map with soil maps have been generated, and from climatic data, rainfall. These all thematic or 7 thematic layers have been stored in a single geospatial data set to reclassify and also resample with the same order and with the same size of the area of the pixels. And within these 7 layers, two models, AHP and FR, have been applied. And for the AHP model, consistency has been also applied to show the is it reliable or not, and as well as based on the result of the AHP and FR, the layers have been weighted and rated, and overlay analysis using raster calculator was applied, and in the final stage, groundwater potential zones have been generated. So at the end of this research, the groundwater potential zones were subjected to for accuracy assessment and validation, and as well as have been stored in a single geodatabase. In general, 90 processing or 90 steps have been implemented during the mapping of the potentiality of groundwater. In this research, it has been started from the critical thinking that why we have selected this subject, literature review, searching, and as well as consequently the preparing of the conventional data. All of them is shown have been shown here. So it means that this research was started from the critical thinking and ended with validation of AHP and FR models using ROC and AUC. What is the concept or the usage of analytical hierarchy process? This is a statistical model which was firstly introduced by Sati in 1980, and generally it is a multi-criteria model for complex decision making through assessing multiple factors. This model is used in different discipline and field based on the applicability. So in engineering disciplines, it's consequently used for such susceptibility mapping, and especially in during the last decades, it also has been used in groundwater potentiality mapping as well. So basically, this model HP consists of four sections: the goal, criteria, sub-criteria, and alternatives. And this study, the aim of this study was the groundwater potentiality or groundwater potentiality mapping. So the criteria was it means that in this study we have selected 7 influencing factors, which are the lithology, slope, renal density, land use, land cover, lineament density, rainfall, soil map. So each of them has their own sub-criteria. For example, lithology, different types of lithology were existed in this area, slope also in 5, but mostly each of these criteria has been divided into 5 criteria as much as possible, except of the lithology. The others are were selected, classified into 5 classes, and as well as the alternative. It means that based on these sub-criteria and criteria, a map was generated to show or based on these 4 alternative: very low, low, moderate, highly. As you can see, the connectors or the relations that each alternatives are followed or affected by each section or each criteria. For example, very low based on the weight or based on the influencing or based on the importance of the lithology, it's somehow affected on all time. For example, lithology is related or is influencing on the very low alternative, on low alternative, on moderate alternative, on high alternative. Consequently, each of these criteria and sub-criteria is somehow related to the alternative. So based on this, 7 thematic layers have been provided in this research. That these are the sources. The lithology has been clipped from the general map of 125,000 taken from the General Directorate of Mineral Research and Exploration of the Turkey, and the pixel then firstly it was converted to the raster. Then each of these 7 layers were resampled into 50 by 50 meters, and as well as the slope was SRTM digital elevation model arc second or 30 meter from Earth Explorer. Drainage density also was generated from SRTM DM, as well as land use land cover was used 2 types of resources: Kurin land cover 2018 and Sentinel-2 MSI. It means that in Google Earth Engine we have tested the Sentinel-2 MSI for land cover, and Kurin land cover 2018. Linear density was also generated from the SRTM DM using the Landsat 8 with the application of the automated linear extraction in PCI Geomatica, and rainfall data was downloaded from Center for Hydrometry and Remote Sensing, which is a globally, and the original data resolution is 1 by 1 kilometer, and so finally the soil depth has been generated from the well logs taken from the responsible departments. So as you can see that the pixel size of each 7 layer has been resampled into 50 by 50. So these are the final map or plotted map of each thematic layer. For example, for lithology, as you can see that the most part of the central Antalya is controlled by the dolomite limestone, and as well as the large plateau of the travertine is existent within this area, and these red points are the log data that have been collected and inserted here for different purposes, especially for the running of the FR model, and as well as the validation purposes have been used these log data. Also the slope map, as you can see that the slope or the slope is ranging from the 0 to 80, that very limited types of very limited parts of the central Antalya and Konyaaltı and Düşümaltı is characterized by the steep slope, that the most part of the central Antalya is controlled by the law. It means that between the 0 to 60 or 20 degree of the slope. In drainage density map also you can see that the drainage, most of the density of drainage are accumulated within the central part of our study area and west part of somewhere here, and the rest of air which are characterized by the steep slopes are not just characterized by the drainage density and land. Here are the about the 7 classes which have been selected during the land use and land cover. That the urban area is observed here only in the eastern part, and from the land use land cover map it's revealed that the most part of the central Antalya is characterized by the vegetations or the greens area. So generally it is the agricultural region. Lineament density also generated from the Landsat 8. As you can see that the most part of the dense area of the lineament is located within the central and southeast part of the study area, and also the rainfall data, the resolution is too less because there was no any I mean that the sources, so that's why we have used from the global data and the rainfall precipitation, average annual precipitation between the 2009 to 2020. It ranges from the 400 to 549 and as well as the soil depth which have been generated based on the well logs. The lithology of the each logs were studied carefully, discussed, then the soil depth data was generated and classified into 3 classes. So once these data were plotted, the main things that we should take into consideration during the running of the AHP model, we have added all the thematic layer, these 7 layers, into a single ArcMap documents. Once again, we check the pixel size to be all of them into 50 by 50 of raster and assigning the rate to subclasses. It is a little bit confused steps that once we should assign the weight, and as well as we should assign the rate for the each subsection or subclasses of the layers. Then via this formula, which is the weighting and rating, or the summation of the weighting and rating. For example, the lithology rating plus slope weighting, slope rating, like this. Using the raster calculator, we have applied and calculated the rand. There is we must pay attention during the calculation of this formula that if we use from the weighted overlay analysis, which is an automatic tools in ArcGIS, this automatic weighted overlay accept only integers, whereas our result will be in doubles. So that's why in this study, in order to exactly achieve the result, we have applied the raster calculator. Here is the final weights and rating. For example, for lithology with these subclasses, each subclass has its own rating and normalized rates and weight, and as well as the slope, the drainage, and here are based on this table weights, we can consider that the lithology has the maximum weights, and as well as the soil depth has in this study has the minimum weights and rating. So the groundwater potential map by AHP has been generated by the running of the this model. As you can see that the map is classified into four classes based on Jain classification, that mostly the coniality by considering the influencing of these 7 layers is characterized by the very low, and some other areas in the northern part, in the western part, and as well as in the southern part are characterized by the low. So the distribution of moderate potentiality is seen in the central of our study area, and as well as in Kapesen Dushamalti. And also you can see the distribution of the high potential of the groundwater. It's mentionable that AHP is based on the knowledge of the authors, knowledge of the analyst, because in the first step you must assign the weight or assign the importance of each factor to the between each others. So in this research, that's why we have assigned one hydrogeologist to take his or her opinion about the assigning of or importance of each factor, and as well as we have taken these factors and raised from the literature. So basically, or we can say that mostly depends on the experience and knowledge of the analyst. The next model is the frequency ratio. It's also the statistical model applied for geospatial assessment to determine the probabilistic relationship between the dependent and independent variables or multi-classified thematic layer. And groundwater also it can be used in different disciplines as the AHP, but frequency ratio is also used commonly in groundwater potentiality mapping to find it's based on the relationship between the distribution of observational wells and parameters influencing on groundwater potentiality. In this area, we have collected about the 141 well data with high yield, and so the distribution of these 141 well data in each subclasses were evaluated and calculated. Then this model was run. Influencing factor in this research is the lithology, slope, drainage density, land use, lineament density, rainfall, and slope soil data. Once we have calculated using this formula, it means that the percentage of the well and by the percentage of the pixels, then we can run this formula. It means that the summation of the all frequency ratio for of the thematic layers. It can be calculated using the automated overlay analysis tool and as well as the raster calculator. In this research, we have used raster calculator because the values are in double, not integer. Here, as you can see, the result of the calculation that, for example, for the lithology, we have the subclasses. Each class is the percentage of the alluvium, and in this area is about 21%. It means that within the alluvium area, from 141 number of wells, only 69 of them existed. It means that within the alluvium area, within the alluvium area, 48%. 48. We have some area, for example, Pebble, Church, Shell. For example, in Shell area, there is no any well data, so that's why the frequency ratio is 0. Consequently, the other thematic layers frequency ratio also was calculated by this way. And finally, the groundwater potential map was generated based on this. Based on this method, the frequency, the very low area have been. It means that most of the area is characterized by the very low potentiality, whereas the less area is characterized within the high potentiality. So by the comparison of these two models and considering of the 7 most influenced thematic layer on groundwater potentiality, these two maps, we can say that the comparison, for example, in very low classification by the AHP, very it means that about 9% area of our study area is characterized by the very low, whereas by the FR model it is about the 46. Or for example in high, it means that it shows that 23% is covered by the high potentiality using the AHP model, and using the FR model only 4%. It means that there are some changes. In order to know, in order to take the decision that which result is reliable, we have applied the ROC and AUC to validate or to find accuracy assessment of each model. Based on this model, which has been calculated, the result the accuracy assessment of AHP result is 56%, and the accuracy assessment of FR or frequency ratio is 65%. It means that based on the validation, based on the accuracy assessment, it's concluded that the result of the frequency ratio or map which have been generated from the frequency ratio is more reliable than AHP. Through the conclusion part, the main important point is that the integration of the remote sensing technology and GIS make tasks easy and accessible for experts to conduct potential mapping with low effective costs and time consumed in a regional, national scale as well. And as well as by giving importance to lithology, high importance, and less importance to soil depth. Within the study area, Murad Pasha, Capiz, and Eastern Dusumalti districts are followed by high potential of groundwater based on the both model. It means that AHP and frequency ratio. So the reason or the logic behind the high potential of these districts are the existence of huge travertine plateau, which makes an environment for higher permeability of the groundwater, and as well as the regions characterized by steep slopes, and as well as the igneous rocks cover are directed to low or very low groundwater potentiality due to huge amount of the runoff on the surface. Also, the regions covered by the agricultural forest area and alluvium have moderate potential for groundwater. So the final result on maps and validation confirms, as I mentioned before, that the maps or the result by the frequency ratio model is more reliable and efficient than the AHP model. And finally, the result from this study can be a hint for the responsible department to have accurate future planning groundwater in terms of the distribution, planning, consumption, and artificial recharge of this area. And at the end, thank you for your attention.